Hello, Year 12. It's me again. So this is going to be the last couple of videos. I'm going to do two short videos, one on 11.8 and then a separate one on 11.9. It's going to be the last two videos in chapter 11 and the last two videos of the year. My goodness. And what I'd like you to do is to make notes on 11.8, refractive index. Then after you watch this little video, and then there's another video I'm going to make on 11.9, total internal reflection. And then you can do all the summary questions, do the optical fibres questions on page 215, and also then, because we're at the end of chapter 11, there's 8 practice questions on page 2, 16 and 17 that you can do and send to me on Show My Homework, and I'll probably make a little video running through all of those so that you can have a look at that. And then summer holidays, and then I'll see you in September, face to face or mask to mask or what have you. Okay, well look, 11.8 refractive index. I made a few notes, so let's have a look at them, shall we? We know that refraction is the bending of light, right? And we know that the bending occurs because of a change of speed. The greater the optical density of the transparent material or medium, two words for the same thing, the slower the light travels in it. So diamond, for example, light slows down a lot in diamond coming from air. So its refractive index is therefore very high. Now, refractive index, little n here, is a measure of how much a material slows light down. To calculate it, you divide the speed of light in air or a vacuum, C, by the speed of light in the material. And you get a ratio, and it's like, it'll be a number ratio greater than 1. So, for example, the refractive index of standard glass is maybe, let's say, 1.42. It varies actually from about 1.35 to 1.5, depending on how much lead you add into the glass. You get lead crystal glass, that is high density glass, has a refractive index of about 1.5, even perhaps 1.6. I don't know, maybe I'm making that up. But anyway, you divide the speed of light in the vacuum by speed of light in the material. Because this might be, V might be 2/3 of C, then you get a number of about maybe 1.4. Let's have a look at it another way round. You could say the refractive index of a glass block is 1.42. What will the speed of light be in it? We could rearrange this. You get your V equals C over N, speed of light in a vacuum 3 × 10⁸ meters per second, divided by the refractive index of the glass block of the glass 1.42, gives us a speed of about 2.1 × 10⁸ meters per second, right? Less. Obviously it's less than the speed of light in a vacuum. That's the universal speed limit. Nothing can go faster than that. The key equation in this topic, refractive index, is Snell's law. Snell's law has been around for 400 years. And what it tells us is that if you multiply the refractive index by the sine of the angle, it'll give you a constant for a given event. Let me explain that. So here, look, we've got a ray of light moving from air into glass. I've written the refractive indices down. Air, 1.00. So the refractive index of air is practically the refractive index of a vacuum, because air is mainly a vacuum, isn't it? The distance between the particles compared to the size of particles in air is very great. So moving into glass, here's my refractive index I used earlier, 1.42, and we know that the ray will bend toward the normal. This is so the boundary between is this hard line, the normal is this dotted line, incident ray, incident angle, refracted ray, angle of refraction. See how it's smaller because the ray bends toward the normal. because we've got this this wavefront coming here. This end will hit the boundary first, and therefore slow down first, and it'll turn like that, right? So Snell's law says n1 sine theta 1 equals n2 sine theta 2. You could write it as n sine theta equals a constant, because both sides of the equation are equal, right? So let's just do a quick example. Let's say the incident angle is 40 degrees. What is the angle of refraction? We can work it out. If we know three things, we can work out the fourth. Let's put the numbers in. So n1, 1.00, sine 40 degrees, incident angle equals n2, 1.42, sine of the angle of refraction. And then let's just rearrange it. For sine theta 2 gives us sine 40 over 1.42. I've ignored the 1 here, the multiplier of 1. And that sine of 40 is 0.6428. Check that for yourselves. Divided by 1.42 and gives us 0.4527. Don't forget to take the inverse sine, or arc sine as some of you people call it, of 0.4527 gives us 26.91 degrees, or 27 degrees to 2 sig figs, because that's what I've got up here. Okay, so that's a use of Snell's law for working out the angle of refraction. And if you know any of these three things, you can work out the fourth. So we could have wanted to know what the refractive index of the glass was if we knew the two angles. Yeah, and we know that the refractive index of air is 1. Okay, all right, that's all for now. 11.8. Go do the summary questions. Enjoy. Bye bye.